All right, so this discussion is going to be centered around resources that teams use, and we use specifically to either design your robot or just keep in touch with the community, or just places you go to learn new things. So it's going to be a little bit all over the place. And I will send out all these links to you in the channel, so you don't have to worry about writing anything down unless you want to. So this first part's going to be specifically for the Richardson students. What I have up right now is the AM14U4 kit of parts chassis. So you will receive the new version of this, so probably the U5, in a box, the U4, Stuart says.
Still the same, still the same.
That's not what I heard. I heard at least it has a couple new holes. But yeah, so it'll be something very, very similar to this.
Yeah.
And so this is your chassis. This picture here shows it with the gearbox mounted in the center with a gearbox called the Tough Box Mini. These motors are sim motors, and you have 3 6-inch wheels on each side. You can play around with what wheels you have, but these are the ones that are going to come in the box. There are belts that drive the wheels from the center, and some structural supporting parts. You'll have a full assembly guide, and all you'll really need to do is decide what size you want to cut it to. You'll cut these front and back pieces and the side pieces. There are different gear ratios you can purchase after the fact for this gearbox if you want it to go different speeds. Say you use different size wheels and you want to, make it a better, speed for that particular wheel size. Like we've used this with 8-inch pneumatic wheels one year. So it's really pretty flexible in how you can use it. The caveat to all this is that and I believe I mentioned this last time, we are going to heavily encourage you to use the EveryBot design. Let me switch over to that. This is the EveryBot's website. After the first week, you'll have pretty good preview of what the EveryBot for this year will look like. This is robots that's designed by a mentor group for rookie teams, for low resource teams. It's very affordable, can be made with hand tools, and it tends to perform very well. So it's a really good place to start an FRC before you really got your head wrapped around it. The EveryBot, you'll have like a video of it after the end of the first week. By the end of the second week, you'll have full assembly instructions, full purchase list, full CAD. And this is built around the kit of parts chassis. So say, after kickoff, you want to go back and you want to start building. Can someone let Ian in? He just messaged me. I would highly recommend that you don't cut the chassis up until you know the size of the EveryBot. So build it at full size if you want to play around with it, get started, with programming, and maybe even get to the point where you're driving it around. But wait to cut it. That's going to be really important. So before I move on, are there any questions specifically about what I've shown so far?
I have a question. So if we're just going to build the every bot with the chassis, what do we want to be doing for the first 2 weeks?
So that's a really good question. I think for any team, regardless of whether they're building the every bot or another bot, they're going to spend a lot of that first 2 weeks, first week especially, working on the strategy, the strategic element. What are we looking at doing for a match? So the every bot will kind of guide you in that direction, but you'll have some flexibility too as to like actually how you are spending those 2 minutes and 30 seconds. There's a lot of work on the control system side. So you'll have programming to get familiar with. You'll have electronics to get familiar with and how the two interact together. The wiring, maybe just on a simple, put a piece of plywood, mount all your control electronics together, wire them up, and then get some, example code uploaded onto those to just get a drivetrain moving. That'll take a good bit of your time, just getting all of the software installed, the firmware updated, and really becoming familiar with that. Outside of that, what a team typically would do is work on building the field. I don't know exactly how that'll work for the RHS team since we will be building the field at Pierce, but you can certainly help with that if you are available to come over to Pierce. I know we're going to be hosting a field build day on the Sunday right after kickoff. So Saturday kickoff, Sunday field build at the Pierce shop. And then, yeah, I mean, there's no harm in jumping into CAD and thinking up some of your own ideas, but it's not necessarily something that you would end up using, which happens no matter what. You're always going to design things that don't get used. That's just the nature of design. Do any of the other mentors have anything to add? All right. That's very funny you asked that question because I actually asked Alan Gregory that exact question when I was down there for the mentor workshops. So there's always something to do. Don't think that just because, we're pushing in this direction that we don't want you doing work. There'll be a lot of, software controls, manufacturing, assembly work to do that you will be busier than you probably ever have been. Okay, so changing gears a little bit, I'm gonna switch over to some of the community resources. The first is called Chief Delphi. This is a little bit of a double-edged sword. This is a discussion forum for everyone in FRC. There are, I don't even know, tens of thousands, hundreds of thousands of threads going all the way back to the late 90s. It's very active, especially after kickoff. It will be extremely active. It kind of gets a little bit funny in the off season. But as a mentor recommending this to, rookie students, I just have to warn you that not all the information is good information. It takes time to build up that experience and that filter as to what information is, beneficial and new and like thought-provoking, and what's, people being sarcastic or doing other dumb things on the internet, or, rookies helping rookies, which doesn't always lead you in the right direction either. So I think on the plus side, it is a net positive for the community. You'll see a lot of good information here. It's just, if you are wondering, whether something is right or wrong, like absolutely reach out to a mentor on the team and we'll be able to guide you in the right direction.
I think my biggest warning I can say about Chief Delphi is a team will post something about something that they're doing and how easy it is, and you just have to do this one simple thing, and look what we got working. Look what this 205-4 team was able to get working. Can we just do this? Because look how great it is. There's a lot of hard work and experience and design stuff that oftentimes in Chief Delphi just gets completely hand waved away, and a lot of hard things that are very, very difficult that they just sort of say, oh, it just works, when it may not. And it is almost worse than a lie, because it's the truth. Someone did get this working, but that doesn't necessarily mean that we're going to be able to get it working as well as that. So there's always that be careful when you see a miracle solution. It's generally a lot more work than it appears.
Yes.
Although sometimes it's not. Sometimes there is the tote stacking passive thing that just scores you tons of points, because here, do this. But it's takes a long time to develop that sense for what is a rabbit hole and what is not.
Yeah, and especially if you're considering like starting a post, asking questions, I would definitely run it. Ask it internally first. We can probably get you a pretty quick answer with more correct information. And every year there's this big thread as to how to use Chief Delphi, and I'll share that once it pops up. But it's basically like read the rules of the game first before you ask questions. That's what it boils down to, because that's really important, and a lot of teams think they can skip that step. This I will share. This is a great thing that's really new. It's called the Open Alliance. It's a group of teams that share throughout the build season pretty much everything that they're doing. So they have this kind of homepage where the teams get set up. There's a Discord. There's going to be Onshape links to their CAD, and it's really great. Teams putting out really great information. So that's always good to follow. I'll be following it closely. Along with Chief Delphi, there is an FRC Discord. It's really intense. I can't even be on it. It's just constant streams of people talking. So unless you want to devote your life to it, it's pretty intense in that sense. It's constant. So if you're not following it, you can get lost pretty easily. But people learn a lot there too. It's a lot more informal than Chief Delphi. The third is FRC Reddit, which is mostly memes. And I'm not going to post a link to that. You can find it on your own. Going from here, I'm going to go over to the Blue Alliance. The Blue Alliance is a website for tracking events and individual matches. So you can search for teams. So we're 1745. Here we can see this is things for 2021 season. I can go to the 2020 season where we actually competed. Here are all the matches we competed in at this event. This other event was canceled. Here's a picture rendering of our robot. I can watch match videos. I can go into any individual match and I can see everything that was scored. There's a whole, I don't know what that is. This was when they were tracking robots on the field. The
zebra motion, they had this whole thing. I really wish the season would have gone further because I think it might have been interesting. I don't know.
There's a whole API behind this, and it's updated live at your events. So after every match, a few minutes after each match ends, you'll have all this information. It can really help your scouts. And you can see live rankings for an event. So here's an event, here's all the matches, here's what the alliance selection was, playoff matches, here's rankings with all the ranking scores, tiebreakers, was anyone disqualified? Here's all the awards that were won, which would show up after the event. Here's how many district points you earned, which again would show up sometime after the event. And even before the event starts, you can see all the teams that are competing at that event. So this is really awesome. There are apps for this for your phone, so you can get it on your phone. You'll definitely want to do that before going to an event because you'll want to be on it. The next one, the Compass Alliance. So this is a resource put together by several teams. This is for guided learning for anything in FRC. So if I click its pathways link, this says, what do you want to learn? Hey, I'm a rookie. I'm going to go to the rookie pathways. And there's this document that shares a bunch of links as to what a rookie might need to know. So, 10 pages worth of links and information that's going to take you through everything a rookie could possibly want to know. If I'm not a rookie, maybe I want to learn about awards, or I want to learn about fundraising, outreach, scouting, strategy, programming, mechanical design, pneumatic systems, CAD. I've never gone through even a fraction of this website. I'm sure the people that run it are very capable, and I would trust any of their recommendations. This isn't exactly new. I have clicked a link before and the link was broken. If that happens, feel free to just reach out to them directly through their website. They have during build season that they call their call center. So teams are available for you to ask questions. I've never used that, but I think it's a good resource for newer teams or teams with fewer mentors or no mentors. But this is a really good place to start your learning. Going to stop again and see if anyone has any questions. I'm just rushing through this because I'm just touching on where you can go to find more information. All right. I'm going to go to our team's public-facing kind of intranet. This is where we put out a lot of information for our team processes. So our students will definitely want to get familiar with this. Anything that we have can be ported over and used for the RHS team. So there are some training things we have linked here, but it's definitely not up to date. But this exists, and it probably needs to be reviewed and updated because it hasn't been for several years.
I've been updating some of the things as they can, but we haven't done a full scrub of it in quite a while.
Yeah. So this is team.piercerobotics.com. If you were to just go to piercerobotics.com, it would take you to a different webpage, which is more for like showing sponsors and parents paying dues and things like that. I'm going to switch over to Spectrum's. Spectrum is a team down in Houston. They have mentor Alan Gregory, who is very good at FRC, and he has developed this recommended, basically recommended resources, recommended learning, a lot of their own training. So this first link is their training, which has very easy to follow training curriculum. Keep in mind that their team might do things very differently than your team, but all the slides are there where he has recorded videos of himself presenting to his team. He has included that. They're very transparent. He's very friendly and would answer any questions that you would have if you did have a question. But this page goes on and on and on. So these are all the mechanical resources, CAD resources, programming resources, control system resources, tools, everything. He has a whole page dedicated to people like sharing their CAD for past years, this CAD collection. That can be really interesting if you want to see how a team actually designed it and not just, you know, a really low resolution video of something. So highly recommend anything that Spectrum and Alan Gregory put out. Going to kind of the last kind of learning-based resource. This is fairly new. This is called the Robotics Alliance Project. They put out a design guide. This comes out of Team 118, also down in Houston. Just one of the best teams in the world. They created this document. I'm not going to open it. It's hundreds of pages. It's really quite a comprehensive look at robot design. It's not something to go into lightly. It's, like I said, it's very long. It's very comprehensive.
Is this similar to the Roboting for Noobs document?
This is like 10 times that.
Oh, okay.
I guess I'll open it. This is, 300 pages long. It's a textbook. So, I mean, it's very, very in depth. Very, very in depth. And they're using they have a lot of pictures of robots, some of their robots, but other robots that were working with teams that they collaborated with. And it just goes on and on and on and on and on and on and on. So this is more something you look at in an off season, not 2 weeks before a competition.
I'm probably going to share that with Maze and Balone and Segura.
Yeah.
See if I can't get some bites.
Yeah, but this is Lucien Junkin. He's the guy who did this. He's a really good mentor. So he and Alan Gregory are the two most recent winners of the Woody Flowers Award.
Yep. 2019 and 2020.
Yeah.
No. Yeah, 2019 and 2020. There was no 21. So yeah, that's right.
All right. So switching gears a little bit, I wanted to show this, especially to the RHS students. Onshape is a CAD program. So CAD is computer-aided design.
Let me ask a question here. I don't think when I met you guys earlier, how many of y'all have had some CAD experience? I think y'all use Inventor or something over there. Oh, are y'all muted? Okay, Inventor and AutoCAD. Okay, but you've had some experience with it. You've done some things. Okay, cool. And Ronald certified. All right, awesome. Good news. Okay, so we're not starting from blank here. That's great. Okay, sorry, Ricky.
Sure. No, I have. No, that's definitely a good question. I will say that Onshape is my very strong recommendation for CAD for FRC. And there are a lot of reasons behind that we can get into, but I will not unless you have questions. It is based in the cloud, so that means there are no files saved on anyone's computer. All of it lives in a team account. So this is my dashboard when I open it up. You can see my recently opened documents. You can see I have a lot of folders. If I drop down teams on the left-hand side, I can go into our team. You can see past robot folders here, different things, shop furniture. If I go into a particular document, so this will be where our robot lives for this upcoming season. We have tabs along the bottom. There's folder organizations, and the entire robot will live in this one document. If someone else were to come into this document, you would see them that they're in here, and you could actually like follow them around and see what they're doing. There's great collaboration features. Nobody has to check out a file. Everyone can use it at the same time. They can't necessarily edit the same dimension at the same time, but they can do simultaneous work. And it is fairly similar to Inventor. It's not exactly the same. There will be things you have to learn, but by and large, if you are modeling things in CAD, the program itself is pretty much the same as any other. There's some different things with the way assemblies are mated together, which you can learn. There's a great resource learning center. It'll take you through how to use Onshape. And then there are some very specific FRC related tools, which I'll get to in a second. The cool thing about Onshape is it's free for education accounts. We'll get you set up with your own team. We'll probably set it up to begin with and hand it off to you. Our mentors can be linked into it, so they can quickly pop in and see if you need some help, if you need some feedback. And we can do it all remotely, and it's awesome. Specifically for FRC, there is something called MKCAD, which is a parts library for vendors that sell specifically to the FRC community. There's an app associated with that that's built into Onshape. And there are things called feature scripts, which are specific scripts. So basically functionality enhancing features. So it's not just like extrude a rectangle, it's like extrude this tube that's like very specific to FRC. And you can learn about those things. One, you can ask us, but second, you can learn about those things by going to this website, Onshape for FRC. And there are details all about that. So here's a blog post on the new MKCAD app, because it's a fairly new thing. And there are links to all the feature scripts. And it just tells you how to get started with it. I know the people that keep up this website because they're also involved with MKCAD, which I am involved with. So if you have any questions, we are the right people to ask. So Onshape is definitely what we're going to push you to use. And unless you have any strong reason not to, we'll go ahead and get that set up for you so you're ready to go at the beginning of the season. But definitely that can be a conversation if you want more information. So I'm nearing the end of the links I've opened. One thing I wanted to hop into next is basically the idea of like a calculator. So this is called Recalc. It is a web page that has links to multiple calculators. So for anything that you might want to do, working with motors and different gear ratios, looking at motor curves, looking at belts, and what belts you would use and what pulleys you would put on it and what the center to center distance would be. This will actually pop out exact links to vendor websites to purchase the right belt. There's arm calculators, elevator calculators, flywheel calculators, pneumatic calculators. This is just one calculator website. Other people have created other ones. I think this one is the best, the most recent, at least. One of the cool things is if I start changing things in here, well, maybe this doesn't do it. If I click this copy link button, not only does it take me to the belt calculator, but it takes me to the calculation that whoever sent me the link did. So I don't have to like re-enter all of the different parameters. I can just copy the link, send it out. You can share it with the team. They can look at it, tweak something. They can share a new link. So that's pretty helpful. So that's all I was going to say on that. I don't have anything open for it, but there is something called the Jvn Calculator, which is a very useful gearbox design calculator. It will help you go from the motors to figure out what gear issues you want to use to move whatever you're trying to move. You enter the weight, you enter how fast you want it to move, or actually it'll output how fast it moves. And you can put in coefficients of friction and motor efficiency, gearbox efficiencies, and things like that. And that's something that needs a little bit more of an introduction. I don't want to just gloss over it. And then there are, I forget what it's called, Stuart. What's the other calculator that we use for drivetrains?
The iLight calculator.
Yeah, so the iLight calculator is a little bit more sophisticated. It actually takes into account your robot's like acceleration, deceleration, to help you determine how fast you want to gear your drivetrain to get from one point on the field to another point on the field in the fastest amount of time. So yeah, taking into account that kind of acceleration phase is pretty important, and sometimes teams overlook that. But there are calculators to help us with that.
And I'm mentioning this to all the students, but especially to the Richardson students who I haven't had the opportunity to work with them on. A lot of engineering is coming up with a generalized solution for something, a calculator, or using someone else's calculator, and then just hammering that and just using all the tools you can to build as fast as you can you're constantly building tools to build robots, to build new tools, to build more robots. I don't want y'all to think that it's cheating or somehow less to use a calculator or to use a set of tools or processes that somebody else has created for you or that somebody else has created, because work is going to rise to its own level. And by using those, you're still going to work just as hard. It's just you're going to be working on other things rather than by hand doing, a gear calculator every time you change your claw center of mass or your arm center of mass.
Yeah, so that's just true in industry as well. Like, you want to use what's available to you. So when I work with different like parts vendors, they have calculators that they provide to all of their customers, and it's a very normal part of engineering. And the other thing to keep in mind is the calculator is only as sophisticated as it's written to be. So kind of keep that in mind. The real world doesn't exactly work the way that a calculator says it should work. Assumptions might be made that makes it easy for the calculator to do its job, but you can't expect the perfection from it. So it puts you in the ballpark of where you want to be. But there's no drag on your robot being taken into account when you're driving around on the field, things like that. And
dynamic loads are hard, right? To the mechanical engineers out there.
Yeah. Okay. So I'm going to pause there. That was way more information than anyone should be given in 45 minutes. Does anyone have any questions?
And don't feel ashamed, or that if you do have a question that's a stupid question, it's not. It's just stupid not to ask the question.
Okay, I know all the peer students don't know most of this too, so you can ask questions as well. When it comes to design, whether that's strategic design, mechanical design, control system design, software design, there's really no good place to start. It's really just throwing you in the deep end of the pool and being here as resources to you, so that we can help you stay afloat. We could literally spend, all 4 years of high school just one-on-one going over all this, and we wouldn't finish. As someone who's been a mechanical engineer for 10 years with a mechanical engineering degree, I'm still learning new stuff all the time, at work and in FRC. The world's just a changing place. There's just like this never-ending, education that is just part of the process, and I think most engineers love that part of it. All right. Again, feel free to interrupt if you do come up with a question. I am going to hop over to an older presentation that I gave called Intro to Robot Design. And this is not something I think we can finish tonight, depending on when we want to call it quits. I don't have a hard stop at 8. We could go to 8:15, 8:30. But I do want to start going through this. And since this is a little old, I may skip over some things that we've already covered. All right, let's get started. So we're going to talk about what design is. We're going to talk about my laws for robot design. Then we'll get into system level design, and then follow that with detailed design. What is design? Design is to solve a specific problem. So we do design all of the time. Typically, these are problems that do not have an answer, one right answer. That's what makes it engineering. And typically, they're problems that have not been solved before. Maybe it has not been solved before by you, and it has been solved before by someone else, but you're not necessarily sure or familiar with the fact that they've solved it. So a math problem is not necessarily a problem of design because, there's a specific answer. But, definitely anything we do in robotics, anything you do as an engineer is design. So just because there is no right answer does not mean there are not better and worse answers. There will be teams whose robots perform better than yours. There will be teams whose robots perform worse than yours. That may be related to the design. That may be related to other factors, luck, driver practice, all sorts of different things can play into how a design actually performs in the real world. Design is inherently innovative and creative. You are doing something that is new to you, at the very least, or new to society, which is, very fortunate to work on things like that. No, Stuart's very fortunate to work on things like that, things that really haven't been done before and are groundbreaking. So anyone who thinks engineering doesn't require creativity is wrong. I don't think I know any engineers who, are not creative. They have to be. If the work that they're doing, is pretty straightforward, it probably could be done by someone who's not an engineer. And so just like art, engineering is very creative, and that's really the mindset you should have about it. Design is a decision-making process. And this is really important. So every step of the way through design, you are making decisions that could have major ramifications later on that you may not realize. It's just a constant, stream of micro decisions that you have to make. Where do I put this hole? Like, do I want a belt that's this long or this other length? Am I going to use this type of shaft or that type of shaft? How am I transferring the torque? How am I, powering it? Am I using an off-the-shelf gearbox? Am I designing my own gearbox? Like, it's just you're just constantly making decisions. And that part of it can be a little bit overwhelming to start out. Just knowing that you have to make a decision just so you can move to the next step. And you can go back after the fact and change your mind. It just depends where you're at in the process, how far you've gone, and how, how large of an impact that specific decision had. In a team or a company hierarchy, the decisions that you're going to make depend on where you live in that hierarchy. So if you are the hands-on designer, you're going to make a lot of the little decisions, where your boss might be making bigger decisions, and the CEO is going to be making really high-level decisions that may not even be specific to that product, but where the product line is going to be in 5 or 10 years. So decision making is a big part of design and engineering. There is no I in design. Design is a team sport. I just want to emphasize that anything that you work on, even if you are the only person working on it, is impacting other people. Whether you are designing something in CAD and someone else is manufacturing it, or it's just, you are designing something and someone else is the customer of that product. And so having kind of a team mindset is really important. Once we actually start, designing robots, it's really easy to get into this mindset that, someone has an idea, so it's that person's idea. And that's just not really how it works. The designs are team designs. Even if one person, said the right words that made you go in that direction, the whole brainstorming process is a collaborative process, and you never know what person's, maybe innocuous, comment, triggered that thought in the other person to have the idea. It's a very important thing to understand. And I definitely, want to encourage, individual students, let's define designs by their functionality and not by who came up with them. So it's not Alejandro's idea, it's the climber that does X or Y. That's my soapbox. Talking about design in the FRC context, it's anything that impacts the final robot. So we're talking game strategy, the stuff we'll start doing at kickoff. It's brainstorming, it's prototyping, and preliminary designs of mechanisms. It's the iteration process that adds detail and improves upon those preliminary designs. The build will impact the iteration process. How easy is it to assemble it? How easy is it to manufacture? There's a lot that goes into design. They actually have, they call it design for manufacturing, design for assembly. These are big topics in the kind of industrial world as to
design for supply chain shortages.
Yeah.
Design for 68-week lead times. Design for your vendor says, hey, I can only get you half of that order.
Yeah, and that comes a lot down to like the trade-offs. So sometimes it's worth it to make something more expensive to manufacture because it has benefits to the design or the product. Other times, the kind of supply chain, the manufacturing is the most important thing. So it just depends on who's making those calls, what market you're trying to serve, that sort of thing. And then, when you get into actually testing and practicing, those are part of the design process. And I think if any of you have taken an engineering class, you've heard the engineering design process, you've probably discussed it. And that's a little bit of what we're going to be talking about now. So yeah, this is a quote from Steve Jobs. Design is a funny word. Some people think design means how it looks. But of course, if you dig deeper, it's really how it works. So we use the word how a lot when we're talking about design. That's all of the details as to how it comes together. Not related to what it does. That's this upfront game strategy. That's the what portion of it. But design is all about the how. How do we transfer torque? How do we move from point A from point B? How do we move a game element from point A to point B and do that under control? So that's design. I think that's a pretty good overview. This is just my 4 bullet point. How do we do design well? Keep it simple. At the very least, if something has fewer parts, it means there's fewer parts to break. You'll hear the KISS principle. I didn't invent that. And it really applies to more than just robotics. Number 2, it's going to break. One of the slides I have further in the presentation is how to break your robot. We want to break the robot. We want it to break while it's in the shop and not while it's at competition. So the better job we can do at that, the better your performance will be at the event itself. So knowing that it's going to break, we want to make it easy to fix. And so designing it to be, come off your robot easily. Like, can you take your mechanism off, just by loosening these 4 or 6 bolts? That can come in handy when you are replacing mechanisms after they have broken or just because you're going to the next version of it. Number 3, just because you can design it doesn't mean you can make it easily or at all. It's very easy to do something in CAD that is not actually feasible. So understanding the manufacturing process is critical to being a good engineer. Whether you make something out of sheet metal, how that would be manufactured, potentially cut in a flat shape and then bends up, or something that's injection molded or something that's machined on a regular manual mill or a CNC mill. Like, how it gets manufactured impacts how it's designed, and so that just takes a lot of common sense and a lot of experience. That's something you will learn, and you will make mistakes. But that's just part of the process. And having gone through that process as a high schooler, will make you very valuable, like later on in college and later on than that in your job. Because I've come across a lot of like seniors in mechanical engineering programs that are graduating and about to enter the workforce that haven't made anything before, and it really shows. And so you're really getting a head start. And I know that you're building stuff in your classes too. That's definitely something that wasn't as prevalent back when Stuart and I were in high school. Number 4, no one makes perfect parts. What does this mean? This means that if you assume that the holes of the 2 parts that you're putting together will be in the same place that the bolts will go through easily, you will be mistaken. Things just come back a little bit different than you have it in CAD. And you can design in such a way that minimizes the impact of that. It's a process called tolerancing. You might hear, I don't know if you've heard this, it's pretty much an industry thing. It's just like geometrical dimensioning and tolerancing. It's called GD&T. It's a whole philosophy of how to tolerance parts so that assemblies can go together.
You can make a lot of money being a GD&T specialist and make machinists cry.
Yes. So this also goes back to, just because you can design it doesn't mean you can make it. It can get really expensive to make things that are tightly toleranced or weirdly toleranced, because metrology is a thing. That's like the science of measuring. So if you design a part and then it gets manufactured, there's a drawing that it has to be inspected to. And so there's literal people that devote their lives to like, how do I measure this to show that I made the part correctly? So that's a thing. It doesn't impact FRC particularly, because we're making like 1 or 2 of something. And if something's wrong, we just, grab the drill and drill the hole out a little bit bigger. But quality matters. So, paying attention when you're manufacturing something, really putting in the extra effort to do things right will really make the assembly go together more easily, and it'll save time because you won't be remaking things. How do you feel about stopping there? Or do we want to keep going?
When do you get where is this the one that has robot units in it?
Yes, that's like next. Robot units.
I personally would like to talk about robot units.
Okay. So
I think it's very important.
Strategic design, we got an introduction to last time. We have resources that are limited in robotics. So those resources can briefly be summed up as time, because our build season is limited. We have to compete in March. We have the people on our team, that's number of people, the level of skill of those people, and then the money, and also kind of factored into that, the resources we have, which could be, what tools do we have at our disposal? What manufacturing equipment do we have at our disposal? So every team is going to have a different amount and distribution of those resources. So honestly, evaluating the resources you have before kickoff is, in my opinion, the most important and most difficult part of design. And like Karthik says, you must know what you want to do before you can figure out how to do it. So that leads directly into robot units, which is how it's just our way of saying how we allocate resources. So Stuart, do you want to talk about this? So
we will talk about this robot unit, or sometimes we'll shorten it to RUs. A robot unit is kind of a shorthand of talking about this, but it's not measurable. it's kind of measurable, but you can't like say, oh, this is 6 robot units or 4 versus this other teams where it's 4. We will make guesses on that and say that a chassis is this or this, but it's all kind of relative to each other and it's relative to your team. We are using absolutes here, but it kind of illustrates the point. So team A, let's call them one of a very good team in the world. They've got 15 units. See a little 15 blocks there. They are an alpha team. They can do a custom chassis. They can do a shooter. They can do they can have an in-game climber. They can do everything on the field, and they have the money, the time, and first, because time is kind of constant. Everyone has the same amount of it. They have the level of student participation and mentor skills, and they have the resources and experience to back that up. They can come out there with an alpha robot and kick everyone's ass. Team B, our team, like they go through the game, they read it, they know exactly what the robot that they know what the winning robot is going to have. They know it's going to be able to do everything, and it's going to be able to do everything at a high level. And we're like, hey guys, if we want to win this competition, we need to build the winning robot. Problem, they don't have the team to build that robot. They're missing the skills, they're missing the experiences, they're missing the mentors, maybe they don't have enough people, whatever. They only have what they have. So when they build that robot, they're not going to build it to completion. They're not going to be able to build it to the quality. Things are going to get skipped, and or it's just not going to get done. An awesome shooter is great once it's done, but until then, it doesn't really work. Team C, in this instance, is a much smaller team. They know what the rules are. They probably know what the winning robot is. If you notice that Team C has less robot units, they have less ability to manufacture and to make something than Team B, but they build with they know what the best for them is going to be. They know, hey, I can't do shooting, but there's this low goal. I can gather balls and score in the low goal and just drive around and still succeed. And a robot that scores points is going to be worth more than a robot that doesn't score point or that never scores points. And that's how you can have examples, especially in FIRST in robotics, where the quote better team doesn't win. The better team is the team that builds to the resources they have and that understands where they are and builds to that.
Yeah, that was great. So going back to something we talked about last week, your robot doesn't have to do everything, but everything that it does do, it should do extremely well. There is little value in FIRST of doing something mediocre. It doesn't provide consistency that a winning alliance needs. If you can only do something 50% of the time, it's just not something you can kind of place your bets on, even though its ceiling might be higher than a robot that does less.
So I'm going to pop in here because Ricky mentioned something that was a discussion that I had with Ricky and some other teams mentors in 2019. He mentioned if something that only works 50% of the time isn't going to be good enough. It needs to work all the time, or 95. Let's say in order that you want to climb a bar, that you have a robot. We did climbing a bar was from 2020. That was a thing. So you have a claw that you want to grab onto. You've got it on a lift. Then you have a winch, and you also have to line up your claw to grab onto it. If each of those mechanisms only works 50% of the time, how often are you going to climb? You got to line up, then your claw has to latch on, then your winch has to go up, your claw has to latch on, and your winch has to pull down. 50%, 50%, 25, 50%, 12%, 50%, 6%. If each of those only works 50% of the time, the total mechanism, the total times you actually climb and hang, 6%. That stuff adds up. So needs to be 100% or near 100% all the way through the mechanisms.
Yeah, and you'll find, we'll get into this a little bit later in the presentation, but building more simple robots allocates more time for that testing and fixing and programming and practicing. That is what brings those mechanisms to that 95, 100% effectiveness. This is getting into the engineering design process. Before we start this, does anyone have any questions? Okay. I guess we'll just go to like 8:30, stop around then. If anyone needs to hop off, that is fine. We are recording this. The engineering design process is a cycle. You brainstorm, you prototype, which is the build phase, and then you test. And as you begin this process, your designs are not going to be very good. It's only through the iterating, whether that's iterating just in CAD alone or iterating through building and testing, that it gets better. And so the more iterations we can do, the better our mechanisms will be. And the only way we get more iterations in a season is by iterating faster. So from a performance standpoint, the best thing we can do is not worry about the perfect, just get it out there and then fix it from there, improve it from there. So that's a really important concept to think about. I think, I think Stuart and I would both say this, like around 5 iterations is what it takes to get to a really pretty decent mechanism.
To start, to have a mechanism, to start getting a mechanism, and you're like, we can go to a first competition with this, and I think we can work with it. Like it's far from perfect, but it's workable. 5 iterations. Like and as a rule.
Yeah, and I'm using the term iteration pretty loosely. So some iterations may happen only in CAD, like you design something and you show it to the team and they're like, no, we need to fix these 5 things. And, using experience to accelerate the process is very useful. You could also take step backs during an iteration. That's just something you have to keep tabs on. If you have your CAD and you make changes, the good thing about Onshape is you can revert pretty easily. So if you do take a step back, don't try to make the thing that wasn't working work. Just go back to what was working and take a separate path.
And that goes doubly so for the coders. Don't throw more effort at hunting down the bug when you had a working set of code. Just revert and figure it out.
As we talk about processes, one thing I want to point out is that the only thing we have control over is our processes. We do not know what game is going to come every year. So we teach things like the engineering design process and the strategic design process to prepare you for anything that can be thrown at you. And in the off season, you can think about this for the next off season, because this off season is basically over. We can prepare you by teaching you how to use tools, how to be safe using those tools, how to use and that's like physical tools in the shop, how to use your digital tools, your CAD and your programming, mechanical design, software design, electrical design, and then the strategic design, and just how do you brainstorm? How do you prototype? All those things have processes that our team can put in place to facilitate solving problems. And there are a million different ways to do all of these things, but we want to set clear processes for our teams so that you don't have to think about too much. You just do X, Y, Z, and you know that you're likely to get to a good place. And this is exactly what those alpha teams Stuart mentioned are doing. They have, the best processes in place compared to the rest of the competition. And I'm sure if you ask them, they'd say they still have a long way to go. So I don't need to get into this too much. Brainstorming, everyone kind of knows what brainstorming means. There are specific brainstorming processes that we can use to make brainstorming more effective. So brainstorming is all about quantity, not quality. Only a small percentage of your ideas will be good. So you want to come up with as many ideas as possible, even all the bad ideas, because a bad idea might trigger a very good idea in someone else's brain. Prototyping, that's how we build things that we have thought of. We want to build prototypes that answer questions that we have about the game. It is pretty well established how to build an elevator, for example. We do not need to prototype how to build an elevator. We can just design it. But every field and every game element is unique. And so we need to prototype how our mechanisms will interact, how that game piece will travel through our robot or come into our robot, how it will leave our robot. So we will target very specific things we want to test. We want to make those test fixtures, those prototypes, very adjustable so that we can slide things around, change them quickly, dial in exactly the dimensions that we want. And then that information will feed in as inputs to a more stable, sophisticated design. And we'll prototype things that just don't work. We'll prototype lots of things that just don't work. One of the things that I think students can find disappointing is when they work on something and whatever it is that they worked on doesn't make it onto the robot. They see that as very disappointing, and it's definitely understandable why you would see that it's disappointing. But that's all part of the engineering design process. The work that you did, even if it didn't physically make it onto the robot, informed other things that did make it onto the robot. I can say as a professional engineer, I would say upwards of 50% of the things I've ever worked on have not even made it to market. Like there's just a huge percentage of just like design waste, if you want to call it that. And that's normal. And that's just something you have to accept if this is kind of what you want to do with your life. And then testing. Testing is a whole another process. How do you know if something's working or not working? In FRC, we can use stopwatches to see how fast it takes something to do. We can use our slow motion cameras to evaluate, what's going on exactly as, a ball gets sucked into an intake. There are processes, and here I'm just calling out one called the 5 whys, is, okay, you have something that doesn't work. It's pretty easy to look at something and say that it doesn't work, but actually figuring out what the root cause of the non-performance is actually kind of something that takes a lot of skill. You'll see a lot of teams making temporary fixes that didn't actually solve the problem. And that's fine at a competition. At a competition, you just want to fix it and like get back on the field and score points. But if you're in the shop, like we need to take time to understand what went wrong, why it went wrong. And, you know, like I said, one of the ways to do it is the 5 whys. The 5 whys is actually pretty funny. It literally is just you asking why 5 times. So you say, why did this not work? And someone, you know, answers, it didn't work for this reason. And you say, well, why did that not work? And you just use that basically toddler type questioning to drive to what actually might be the root cause. So yeah, root cause analysis is a thing. You know, anytime the robot doesn't perform well, it's definitely something to mention to the other members of your team and your mentors, and not just fix it, because you might see a bolt that's loose and so you just tighten it. But if you had mentioned that to someone, they might have told you, hey, you need to put Loctite on that bolt. Like there's just things that you might not know that would result in better design or better performance. Oh, I hate this slide. I am skipping it. I do not like weighted objective tables. Some teams really like them. I am not one of those teams. I think this is the last slide in, oh, okay, we'll get through these next 3 slides. Systems integration. We're going to break into subgroups to design different mechanisms. It has to be that way, but there has to be some person or group of people responsible to actually making sure all those things work well together. That can be one of the trickiest parts of robot design, especially if you have like game elements like traveling from one mechanism to another mechanism, like this past 2021 year, there were lots of shooters. So they had intakes, which were taking the, the balls from the floor, putting it into their hopper where there were, 5 balls, and all 5 of those balls had to be indexed correctly up into a shooter. And so there's lots of risk at those transition points between the intake and the hopper and the shooter, where something could go wrong. And if the people who are designing the mechanisms individually are not communicating properly and working together properly, you'll show up at competition with, elements of the robot that all work really well individually, but don't work well together. And this is really calling it a full-time job. So, either this could be your coach or mentor, or like your senior, your most skilled student who should be handling the system integration and overseeing your subsystem and system testing. So we want to be giving this person the responsibility to be looking at and handling the top level of their CAD. They will be working from the start as to assigning I'm gonna call it real estate, but it's space in the robot volume for each mechanism to live. So they have to coordinate between the different prototyping teams as to how big something could be, or this can be in this location, but it can't be in this other location. And you just have to really have that foresight to allow everyone the space to excel, but also not, shortchange one group over another. Rule and inspection compliance is very important. Looking at your overall weight, there is a weight limit, there are size limits, and you do not want to be showing up to a competition outside of those specific inspection areas of your robot, because they won't let you compete until it's fixed. And that's something that rookies especially haven't gone through that inspection process, and we can guide you through that. Everything's in the rules, you just have to read the rules and understand the rules. And then, you know, I was kind of talking about this from a mechanical perspective because I'm a mechanical engineer, but mechanical and electrical combine along with software to become controls, and how different parts of the kind of different like engineering sections of the product come together is also something that is part of systems integration. There will be, or there could be sensors on your robot that facilitate your robot doing different things, checking for the presence of, you know, a game element. So the driver doesn't have to look at it. The robot knows. Those can be really powerful tools to have in your tool belt. And having them all work together is something that needs to be coordinated at a systems level. Once the system is built and you have kind of your first prototypes, your first iteration of your robot together, we want to break the robot. This is sometimes very shocking to someone who just built their first baby, and now we want to break your baby. But it is a very important part of the process. I remember a time, Stuart will remember this, where this was 2017. We had a student design like a structure to mount the climber to. And he comes to us and he says, "Hey guys, it's done, like, come check it out." We kind of take a look at it. We're like, this isn't really strong enough to hold the weight of the robot. And at that point, Stuart proceeded to literally break this mechanism off the robot with his bare hands. And it taught a very important lesson. But that's what we're talking about. We want to break the robot. We want to drive it into a wall. We want it to fall apart. And we want that to happen in the shop, because it's okay if it happens in the shop. We can take that feedback, that real-time feedback, and feed it into our next iteration and make it so much better. Because it's going to break, and we have some level of control over when it breaks. This is a process known as continuous improvement. It's part of the engineering design process. And as we are testing things, your drive team is getting practice. They need practice too. They need time with the robot. They need to understand how things are working and become familiar with it. That's just an important balance that your team is going to need to find every year. And just because you do it well one year doesn't mean you do it well the next year. Does anyone want to add on to that? This is like a really important slide. All right. And this is the last slide of the system section. Again, we did not invent the engineering design process. There are resources linked here for talking about system design, engineering design, specifically for FRC. Good resources come up every few years, and I try to keep, especially when I update these presentations, I try to keep them updated. But you'll see some of these are quite old, and that's because they're kind of at the forefront of the movement of doing this kind of design process work for FRC. And the things that change tend to be more on the cutting edge. So like now there's a lot of more, off the shelf FIRST style parts. There's a lot more, vision and sensor stuff in FIRST that may not get covered by some of these resources, but they're still really good resources. Yeah, Stuart says, if he can break something with just his hands, it's definitely not going to support your whole robot. So we'll end it there. If anyone wants to stay on, ask questions, I'm happy to do that. The next time we meet, which might be Wednesday, I might be scheduling our next one for Wednesday. There's that's just when we'll continue on this line of training. I'd love it if you ask questions. I really want you to be engaged with this. I know that just listening can kind of be one ear and out the other. The biggest, learning process will be once you start building your robot. There's just no replacing that at this point in the off season. And Stuart did make a really good point when he talked about static versus dynamic forces. Impacts and shock loads are significantly higher than static or slow acting forces and loads. It's just, if you start measuring them, you can really be shocked. I worked on a project with the UTD, like senior capstone project, and they were measuring impact forces of dropping this really light object from like 3 feet off the ground. And they were measuring like 1,800 Gs. It was kind of incredible how fast something is decelerating and how, your design, potentially has to be able to withstand those kind of forces. All right. Is this useful for everyone? Show of hands. I got a couple yeses. Awesome. And I will send out links to all of those resources I showed at the beginning, as well as this presentation. And if you have the time or the interest, don't hesitate to get ahead of me. The things that I'm going to be presenting are things that I think are especially important, and it's okay if you hear them more than once.
Yeah, I'll rewatch that Karthik. Every year I'll rewatch the latest one, and there is stuff every year that I key off of that has probably been in there for 5 years, but I've just never had the experience where I'm able to notice what he's saying.
Absolutely. Yeah, I definitely rewatch that every year. And everyone should be in that FRC 2020 channel. So that is where I will share this. I'm going to stop the recording.